Hi, in this video of Inkpot, we are going to be discussing matrices. This is the first unit of MV2, and we are going to start with the definition of matrices. We are going to focus on the different types of matrices. This will be a two-part video since the different types of matrices are going to be covered in two parts, and the two parts would be followed by an assignment on the different types of matrices. So yeah, let's get started. Now, the first thing to understand is what is a matrix. And a matrix is essentially a set of ordered numbers which are listed in a rectangular form. Now, this is something that you would be very familiar with in terms of, the way it's been represented. But it's always important to remember two things. One is, that any matrix is represented by, the order of any matrix is represented by the number of rows and the number of columns that it has, which is given by m cross n in general. So m here is the number of rows and n here is the number of columns, and along similar lines, any general element of a matrix is represented by aij, where I represents the row and j represents the column. And it's important that you don't mess these two up. So either you familiarize yourself with them enough that you don't forget them, or you memorize them. Ideally it should be the former. So this is what you have, and it's important also that you don't confuse a matrix with a determinant, because a determinant is essentially a number which is associated with the matrix, and it's not a matrix itself. What a determinant is and how it is calculated are things that we'll get into later, but it's important to remember that a matrix is not the equivalent of a determinant. So these are some examples of matrices. That is 2 cross 2, 4 cross 1. It's always important, to iterate that any matrix with a single column is a column matrix, and any matrix with a single row is a row matrix. And these are the kind of terms that are generally used to represent these. Okay. Now we come to different types of matrices. The first one that we start with is a square matrix. Any matrix which has, the m equals to n is, essentially a square matrix. So when you are representing a square matrix mathematically, all you will say is that a matrix which has m equals to n, which that is the number of rows is equal to the number of columns, is a square matrix. And, these are some examples. Again, this should be extremely familiar to you. Now, the diagonal matrix that we come to next is essentially a square matrix where all the non-diagonal elements of the matrix are 0. Now, to remember something like the diagonal matrix, the way I see, it very easy is to remember that, when you say diagonal matrix, the entire weight of the matrix is on the diagonal, which means that everything else is going to be 0, right? So even when you're representing it mathematically, because in a square matrix the diagonal entries are going to be I equal to j, you actually represent this matrix by saying aij is equal to 0 for all I not equal to j, which means that all the non-diagonal elements are necessarily going to be 0 for it to be a diagonal matrix. And it's always crucial to remember where you're starting from. So for a diagonal matrix, the starting point is a square matrix. For a square matrix, the starting point is m equals to n. Now, similarly, as for a scalar matrix, the starting point is actually a diagonal matrix, right? And for a scalar matrix, essentially if all the diagonal elements are equal to a particular number, then it's called a scalar matrix, and that number is referred to as a scalar. For example, if d1 equal to d2 equal to d3 were, let's say, something like 3, then it would be a scalar matrix, and the scalar here being referred to would be the number 3. Now, similarly, for an identity matrix, once again, you start from a diagonal matrix, which in itself starts from a square matrix, and in their identity matrix, the diagonal elements are equal to 1. Similarly, in a null matrix, the diagonal elements are also equal to 0. So here, you can say that a null matrix is also trivially a diagonal matrix. Now, a null matrix is essentially a matrix of zeros, in case, that's something that is a little bit of a confusion. Okay. Now, like I had said earlier, row matrix and a column matrix are essentially matrices with one row and one column each, and it could have any number of the other kind. So Now, the next matrix that we come to is a zero matrix. So, if all the elements of any matrix are zero, then it is called a zero matrix, and or it's called a null matrix, as we had discussed. So the next type of matrix that we come to is actually an opposite matrix. Now, and any matrix is called an opposite matrix if all the elements of a matrix, are multiplied by a negative sign, then you get the opposite of that particular matrix. So essentially, if you have something like aij is equal to minus of aij, then this matrix or this matrix respectively are called the opposites of each other, right? And this is, I mean, easy enough to understand. It goes back to the inverse concept, not the matrix inverse, the mathematical inverse concept. Matrix inverse is a completely different concept. Now, for a transpose matrix, if you convert the row to column and column to row, or vice versa, then what you get is the transpose matrix. And this is, for a 3x3 matrix, it's probably a little harder to see, but if you have something like a1 is equal to any matrix, let's say a is equal to 1 2 3, the transpose of this is going to actually be 1 2 and 3. So row matrix becomes a column matrix and vice versa. And for a 3x3 matrix, you can see that the elements have actually been flipped, and so on and so forth. Now, for the rules of transposition, it's actually something that's very important, because this is something that you will use in different kinds of uh, problems later. So the transpose of a transpose is actually the matrix itself. So A transpose transposed is A. This is easy enough to see if you take a small example of it, but I would suggest doing it in case this is something that you're not very familiar with. Now, A plus B transpose is simply A transpose plus B transpose. So this is just a simple addition property. Again, easy enough to see if you want to take an example and check for yourself. Any matrix multiplied by a scalar alpha A transpose is actually, so there is no impact on the scalar whatsoever. The scalar remains as it is, and just the matrix gets transposed. Similarly, you can see here. Now, this one is actually very important, because it's saying that when you have two matrices which are multiplied with each other, which are, let's say, A and B, then the transpose of this multiplication is not A transpose B transpose, but it is instead B transpose A transpose, which means that the order actually gets flipped. And this is very important to remember, because this is something that you will be using. Even if you don't use it, this is something that you're expected to remember as a very important property of transposition. And you will be definitely using it in some proofs later. So again, this is something that is easily provable, although the proof is something that you don't need to know. So if this is something that doesn't make too much sense to you, I would again suggest take an example, see for yourself. Okay. Now we come to a symmetric matrix. Now again, for a symmetric matrix also, you are starting from a square matrix, and any square matrix is said to be a symmetric matrix if it is equal to its transpose matrix. So if A transpose is equal to A, then what you have is a symmetric matrix. On the other hand, for a skew symmetric matrix, if your transpose is equal to negative of A, or the negative of the matrix, then you have a skew symmetric matrix. And these are the properties. So again, note that this is the general form in which it is represented, and this is something that is important to remember. For a skew symmetric matrix, Aij is equal to minus Aji. On the other hand, for a symmetric matrix, Aij is equal to Aji. This is something you should remember. Now, an identity matrix, as we had discussed earlier, is a diagonal matrix with all the diagonal elements equal to 1. It is also known as a unit matrix. Okay. The only reason it's been separately put in here as different type of matrix is because I wanted to show you that an identity matrix of any order can be represented by just I3 or IN, or so for example, if you had a 4x4 identity matrix, the diagonal elements would all be 1. It would be a 4 cross 4 matrix, and it will be represented by I4. The reason you don't need the second number here, 4 cross 4, is essentially because you are starting with a square matrix or a diagonal matrix which starts with a square matrix. So this is something that is implied. Now we come to an invertible matrix. Any square matrix A is called, an invertible matrix if AB is equal to BA is equal to the identity matrix. So here B is known as the inverse of the matrix A. Now, matrix inverses work in a different way than, how mathematical inverses in general work. So this, how you calculate the inverse of a matrix is something that we will come to at a later stage. But this is just to prove, just to introduce you to the concept that there is a, when you say that any matrix A has an inverse B, then what you mean is that A into B is equal to B into A is equal to the identity matrix I. And naturally, as you can see, because the multiplication is actually giving you a square matrix, which is the identity matrix, inverses exist only for square matrices. You cannot have a matrix which is non-square which has an inverse. I mean, you cannot calculate it. That's the point here. Okay. Now, this is a very small example. For what value of beta is the following matrix symmetric? Now, recall that, a symmetric matrix is represented by Aij is equal to Aji. So, something like beta square minus 1, which is, this is something like A12 is equal to A21. So, beta square minus 1 is equal to 2, which is beta square is equal to 3. Beta is equal to plus or minus root 3. So, for these values, this is going to be a symmetric matrix. Now, we come to the concept of matrix operations, okay? And let's say you have a matrix A and a matrix B. We define the sum of the matrix, A and B as, the M cross N matrix Aij plus Bij, which is simple enough to understand. You simply add the corresponding elements of the two matrices. Similarly, if you have alpha as a real number, then alpha Aij is very simply, every corresponding element of the matrix multiplied by alpha. For example, if you have something like A given by this matrix and B given by this matrix, if you wanted to compute something like A plus B, A minus 3, or, whatever these are, like I said, you simply add the corresponding elements. So A plus B would be something like 1 plus 0, which is 1, 2 plus 1, which is 3, 0 plus 2, which is 2, 4 plus 1, which is 5, minus 3 plus 0, which is minus 3, and minus 1 plus 2, which is 1. And, so on and so forth. Now, the rules for matrix addition and multiplication by scalar or in general is given by these following rules. Again, these are very intuitive, so I'm not going to go into the details of each one of them. I have just put them here so that this is something that you can refer back to in case it's required. Now we come to the concept of matrix multiplication. Again, this might be something that you're very familiar with if matrix is something that you've dealt with before. In case it isn't, I am going to take one example here and perform the multiplication, just so this is something that you become familiar with in case you aren't. Also know that if this is something that you're not very comfortable with, this is something that you will have to practice and get comfortable with, because this is considered one of the basics, which is kind of, thought of as you having known for a longer period of time. So if this is something that you're not familiar with, I'd suggest practicing it out. Now, essentially, in any matrix multiplication, the idea is to remember the inverted L rule. Okay. So for example, if you look at these two matrices here, the first thing that you need to do when you're starting a matrix multiplication is to check if the order of the matrices even makes it possible for there to for a product to exist. So how you do that is, if you have something like two matrices which are M cross N and N cross M, then this multiplication is going to be possible. Essentially, the number of columns in the first matrix need to be equal to the number of rows of the second matrix. This number can change, but this number cannot. This could be A cross N and N cross B for all we care, but this needs to be there for you to be able to say that the matrix multiplication is actually possible. Now, why I said the inverted L needs to be, understood is because if you look at it, so you have a horizontal, so an inverted L will look like this, right? So you go row wise and then you go column wise. So the first matrix you consider the row, the second matrix you consider the column, and you essentially just multiply the corresponding elements. So the first A11 here is actually multiplied by A11 here, A12 here is multiplied by A21 here because you're considering the column. And A13 is multiplied by A31 here because once again, like I said, you're considering the column here. So it's this column vis-a-vis this row, and this is exactly what is happening, and you then add these up and this is how you get the product. So this is also written here, and you do this for each of these, so the first element would be this, the second element would be this and this, the third element would be this and this, the fourth would be this and this. So this is how you would carry out a matrix multiplication. Now you come to the power of matrices. So if A is a square matrix, then you can write A into A as A squared and A into A into A as A cube and so on and so forth. And this actually gives rise to two other different kinds of matrices, which is, the first one is an idempotent matrix. So you say that, if A is a square matrix, then the product of A by itself is called an idempotent matrix. Okay, so if A squared is equal to A, then A is an idempotent matrix. And similarly, by that logic, A to the power n is equal to A, then it's an idempotent matrix. This is the general form of an idempotent matrix. Again, this is something that you should remember. For an orthogonal matrix, then what you have is that if A into A transpose is actually equal to I, then you have in front of you an orthogonal matrix. This is also to say that here the matrix transpose is actually the inverse of the matrix itself, because if you remember, the condition for the inverse was that A into B is equal to B into A is equal to I. Okay. Now we come to the last question for this video, which is if you're given a matrix A minus B, B, A, you have to prove that this matrix is orthogonal if and only if A square plus B square is equal to 1. To prove this, what you can do is obviously first of all calculate the transpose, which is going to be A minus B and B A. And you do A into A transpose, which is going to be A B minus B, B A into AB minus BA. Okay, what you have is going to be, so again you follow the inverted L. I'm just going to change colors here so that this is a little clearer. Okay, so you have A square minus plus B square, because you have minus B into minus B, and you have AB minus BA, and you have AB minus AB, and you have B square plus A square. So what this gives rise to is actually A square plus B square, 0, 0, A square plus B square. Naturally, for this to be equal to I, A square plus B square has to be equal to 1, which means that for it to be an orthogonal matrix where A into A transpose is equal to I, A square plus B square needs to be equal to 1. So this brings us to the end of this video. We are going to continue with other different types of matrices in the next video. Thank you.